Right, one advantage of treating cancer internally is less healthy cells are killed, okay? A disadvantage of treating cancer internally is scars and a chance of infection, okay? The advantage of treating cancer externally is less invasive, faster recovery. The disadvantage of treating cancer externally is it's more difficult to find, okay? So, just several of those things you need to be aware of in your exam. So cancerous tumours can sometimes be treated using gamma ray therapy. Gamma ray beams are sent through the body at different angles. This happens inside a large circular machine. Okay, on its own, each beam of gamma rays has too little energy to harm the body or the cancer cells. However, the beams are aimed so that they cross at the point where the tumour is, so the tumour cells are killed. Okay, so we've got a diagram of it here. Okay, so for the patient on the right, work out 4 beams to treat cancer tumours in the organs in A, B and C below. Write down 4 2-letter control codes you would need to type into the machine for each tumour. Okay, so obviously for the throat, which is there, okay, so we're going to do C and R. So if we've got C is here and R, so we're going to obviously send one ray there, okay, D and S there as well, okay, and so on. If you followed that, you can pause the video, but basically we can direct our rays to the specific regions to ensure we're killing the tumours or destroying the tumours rather than the healthy cells around them, okay. So you got them for the kidney and testicular region as well, okay. Right, let's have a look at this then. So if the patient is injected with a radioactive tracer, remember we're going to talk about radioactive tracers now, okay? A radioactive tracer will undergo beta plus decay, okay? When it undergoes beta plus decay, okay, it's going to annihilate, okay, with electrons around it, okay, which is this point here. When a positron meets an electron, they're both destroyed. They annihilate and gamma rays are emitted, okay? So in this particular case, you're going to get gamma rays emitted, one gamma ray emitted there, another one here, okay? And we've got this circular ring which can receive gamma rays from all directions. The computer's then going to map out an image of where that tumor is, okay? So in this scanner, this PET scanner, we can identify the regions where we've got tumours. And with tracers, essentially they're radioactive particles with probably some glucose molecules attached to them, and tumour cells want glucose because they're mutating, so the tracer is going to be passed on to the tumour quite quickly. So that's how we know the tracer will get to the tumour. Okay, so as I said, the PET scanner moves around the patient to detect a lot of these pairs of gamma rays, and then the computer can build up an image of the inside of the patient. Why do the isotopes used in the PET scanner need to be made nearby? I've talked about this. So they have a short half-life, so they cannot be transported a long distance, okay? Right, we're now going to be looking at the advantages of nuclear power to generate electricity. Okay, we've already talked about this in a previous video, but they do not release carbon dioxide or sulfur dioxide, okay, which contributes to global warming and acid rain. It's also extremely reliable and produces a lot of energy per kilogram of fuel, okay. Disadvantages are the waste is radioactive. It's got to be put in a specified area underneath the ground, but it is radioactive for a very, very long time. So if any human digs that radioactive waste, he or she is going to be exposed and obviously get cancer possibly. It is non-renewable, so it will eventually be used up, okay? And also, if things go wrong with the power station, we can get a nuclear breakdown and we can essentially cause a huge problem for the local environment if the radioactivity gets out. So nuclear fission, nuclear fusion, and radioactive decay all give out energy. Okay. In induced fission, okay, so this is a controlled form of fission. Remember we said we can get neutron decay, okay, as one of our radioactive decay equations. We start off with the neutron hitting a heavy nucleus, so an example here would be uranium-235, okay. That slowly becomes more unstable because it's got one excess neutron, which is the momentum has passed on to that atom, okay, into the nucleus. That is going to cause the uranium-235 to split into two daughter nuclei. You don't need to know their names, but to split into two daughter nuclei, and 2 to 3 neutrons are then also emitted, okay? These neutrons can then reach other uranium nuclei close to the neutrons, okay, which can then further split, and then we get what we call a chain reaction, okay? And huge amounts of energy are released each time the nucleus splits, okay? And that's why it's so important. And obviously that thermal energy that gets released will heat up some water, which will cause steam to turn some turbines, and that will turn a generator, and we'll get electricity. Let's have a look at the inner workings of a radioactive a nuclear reactor. So, several terms you need to know is, first of all, our fuel rods are obviously our uranium nuclei, so that's what they're gonna that's what's gonna be split up, the heavy nuclei, okay? Now, there are two other things you need to be aware of: the moderators and the control rods. So moderators are essentially a fluid, generally water, which slows down the neutrons that gets released, okay? So essentially it's just to control the fission reaction, which is obviously the splitting up of the heavy nuclei, so that it's not like a nuclear bomb, which is uncontrolled. We also have control rods, which are generally made up of boron. Okay, these will absorb the neutrons. So if you want to slow down the reactions, we will just cause these control rods to fall down, which will, so that we get the chain reaction actually slowing down. If we want to speed it up, we move the control rods upwards, okay? Again, I've talked about electricity being created by the turbine rotating, which rotates the generator, and we get electricity being generated. Right, I'm now going to talk about nuclear fusion. So in nuclear fusion, we get two small nuclei, generally lighter nuclei, joining together to form one large nucleus. And in this process, believe it or not, we get a huge amount of energy, much more than nuclear fission. Okay, this process occurs in stars like our sun. Okay, and however, the conditions needed for this to occur is extremely high temperature and high pressure as well. Okay, so at the moment, engineers and scientists are trying to replicate this on our planet in an efficient way. Okay, so we know how to do it, but it's just really hard to actually get more energy output than we put in to get those starting conditions. So again, the difference between nuclear fission and fusion is that fusion is joining up of lighter nuclei, and fission is basically the splitting up of heavy nuclei. Okay, again, if we look at this nuclear equation, essentially similar to the decay equations I showed you earlier, kind of like maths, 1 plus 1 has to equal 2 plus 0, okay? 2 plus 3 has to equal 4 plus 1, okay? We know the neutron that gets released has a mass number of 1 and an atomic number of 0 because there are no protons present. So nuclear fusion of hydrogen doesn't happen at low temperatures and pressures. The protons in the nuclei are positively charged and like charges repel. So they need to get extremely close to fuse, but as they get closer to the electrostatic force increases. So essentially, we need these high temperatures and pressures in order for this to occur. The Sun has a very strong gravitational field which forces the nuclei to be very close and more likely to fuse. So obviously this is what starts the process in stars, but on the Earth we've obviously got to use other ways of causing the nuclei to join together. Okay, so sometimes we use magnets, and there's various things that scientists do. What does a high temperature mean in terms of particles? Well, it means the particles have a high average speed, a high kinetic energy. Okay, why would high temperature make fusion more likely? Well, they're traveling towards each other faster and are more likely to meet and touch. What does a high pressure mean in terms of particles? Well, lots of particles in a small space, which means a lot of collisions per second. Why would a high pressure make fusion more likely? Well, we're going to get, if you have more collisions, they're more likely to fuse together, okay, if they're more close together. Why isn't nuclear fusion used in power stations? Well, it requires much more energy than it produces, and reaching the high temperatures and pressures is difficult, and it costs a lot of energy and money.